All right, today we're pulling back the curtain on some real hidden giants of the industrial world, fans. And no, I'm not talking about the little thing on your desk. I mean massive, incredibly powerful machines. These things are the unsung heroes behind, well, pretty much everything from making our power to building our cars. So let's dive right in.
It's a really cool question to think about, isn't it? Because in a very real sense, these power plants do breathe. They're constantly inhaling these gigantic gulps of fresh air and then exhaling exhaust. And we're talking on a scale that is just mind-boggling. And what acts as the lungs for these massive industrial beasts? Well, it's a whole team of super powerful, perfectly coordinated fans.
Okay, so before we get deep into the power plant stuff, let's pump the brakes and go back to basics for a second. What exactly is an industrial fan? What makes it different from other things that move air around?
Really, the key difference boils down to one thing: volume versus pressure. See, a fan's whole purpose in life is to move a ton of air, a huge volume, but without really squeezing it. I love the analogy of a river. You've got a massive flow, but not a lot of pressure. Now, a compressor, that's the total opposite. Its job is to take a smaller amount of air and squeeze it like crazy to build up really, really high pressure. So yeah, totally different tools for totally different jobs.
So when you're faced with the challenge of moving all that air, engineers basically have two main philosophies, two fundamental ways to get it done. And it all comes down to a simple question: which direction are we going to push the air? Let's take a look at what that actually means.
And here they are, side by side. On the left, you've got the centrifugal fan. See how it sucks air in right through the middle and then, whoosh, flings it out the side at a 90-degree angle? Then on the right, you have the axial fan. This one probably looks more familiar. It just acts like a propeller, pushing the air straight through, in line with its axle. As you can see, two completely different ways to get the air from point A to point B.
Okay, let's zoom in on that centrifugal fan for a minute. The name gives it away, right? It works using centrifugal force. You know that force that keeps water in a bucket when you swing it over your head? Yeah, that's the one. So air gets pulled into the center of this spinning wheel, which is called an impeller, by the way, and then it gets thrown outwards with a whole lot of force. And it turns out this design is absolutely brilliant for building up higher pressure.
Now, the axial fan, this is the one we all kind of know instinctively. The fan that cools your computer, that's an axial fan. The one behind your car's radiator, axial fan. The design is really simple, it's pretty cheap to make, and it is perfect for those jobs where you just need to move a bunch of air, high flow, without needing to worry about creating a lot of pressure.
Okay, this is where things get really, really interesting from an engineering perspective. Because when we talk about centrifugal fans, the shape of the blades inside that spinning wheel, it changes everything. We're talking about how a tiny change in a curve can be the difference between a fan that runs at peak efficiency and one that literally burns out its own motor. The stakes are that high. So first on our list is the backward curved blade. Now, take a look at that performance graph on the right. See that horsepower line, the one labeled HP? Notice how it goes up, but then it levels off and actually starts to dip back down? That little dip is huge. It's called a non-overloading characteristic. And what it means is that no matter what happens with the airflow, the motor will never try to draw more power than that peak. It's like having a built-in safety fuse. Honestly, this design is pretty much the heavyweight champion of performance. We're talking incredible efficiency, sometimes over 90%. Plus, it's super stable and runs quietly. You put all that together with that amazing non-overloading power curve, and you've got the perfect fan for clean air systems. Anywhere you need top-tier performance and absolutely no nasty surprises. All right, now let's flip the script and look at the total opposite, the straight or radial blade. The design looks really simple, right? But look at that horsepower curve over on the right. See that? The HP line just goes up and up and up. There's no peak. That is what you call an overloading curve, and it's dangerous. If something in the system changes and the fan starts moving more air, it's just going to demand more and more power from the motor until, poof, it could literally destroy itself. So you might be asking, why on earth would anyone use a design like that? Well, the answer is simple, because it is tough as nails. Those simple, rugged blades are fantastic for handling dirty air filled with stuff like dust or wood chips, abrasive particles, and they're a breeze to maintain. It's just a classic engineering trade-off, right? You give up some efficiency and that safety feature in exchange for raw durability in a really nasty environment. And last but not least, we've got the forward curved blade. You can really see how the blades are shaped almost like little scoops designed to just grab the air and fling it in the direction it's already spinning.
Now, this design also has that great non-overloading power curve we saw earlier, but it's got a few other tricks up its sleeve. This blade, it's a specialist. It's a master at handling dirty, abrasive gas. And here's the really cool part. Because of that scoop shape, it's actually self-cleaning, so material doesn't build up and cake onto the blades. It's kind of the best of both worlds. You get that built-in motor safety from the non-overloading curve, but you also get the ruggedness you need for those really grimy jobs. All right, so now we've got a good handle on the different fan designs, right? We know about centrifugal versus axial and all the different blade shapes. So now, let's see them in action. Let's put them to work in one of the most demanding places on Earth, a steam power plant. Because here these fans aren't just moving air, they're working together like a giant mechanical respiratory system. It all starts with the inhale. That's the job of the forced draft fan, or FD fan for short. This thing is grabbing enormous volumes of regular outdoor air, ramming it through a heater to warm it up, and then forcing it right into the furnace. This is the fresh oxygen that the fire needs to burn.
Okay, next up is the primary air fan, the PA fan. And this one has a very cool, very specialized job. It takes air and heats it up to insane temperatures. We're talking over 600 degrees Fahrenheit. And it uses this scorching hot air as a delivery service. It blasts that air into a machine called a pulverizer, where it instantly dries out crushed coal and then carries that fine coal dust directly into the furnace to be ignited. And of course, what goes in must come out. This is the exhale, and it's handled by the Induced Draft, or ID fan, which is usually the biggest and most powerful fan of them all. Its job is to be at the other end of the system, sucking all that hot, dirty exhaust gas and ash out of the boiler. By pulling all that stuff out, it actually creates a slight vacuum, a negative pressure inside the furnace, which is absolutely critical for keeping the whole process safe and under control. Then it sends all that exhaust up the smokestack.
So, we've seen what these amazing machines can do. Now, let's just finish up by taking a quick peek inside to break down the parts that make it all happen. So here you have it, a complete industrial fan assembly. You can clearly see that big green housing, which is called the casing. Then there's the blue electric motor that provides the muscle. And if you look right through that opening in the front, you can see the red fan wheel itself, the impeller. I know it looks like a lot of parts, but how it works really just boils down to 3 simple steps.
The whole process is super simple, but incredibly effective. First, the motor spins, providing the rotational power. Second, that impeller, the wheel with all those different blade shapes we talked about, takes that spinning energy and transfers it directly to the air, getting it moving. And finally, step 3, the casing, or the housing, gathers up all that moving air and points it exactly where it needs to go. That's it. Power to movement to direction. That's the heart of it all.
And that pretty much wraps it up. It really makes you think, doesn't it? We look at a fan and think, oh, that's simple. But lurking just beneath that simple idea is a world of complex fluid dynamics, advanced materials science, and some really clever systems engineering. It leaves you with one final thought, one last question. What other supposedly simple things are all around us, just hiding the same level of incredible critical engineering waiting for us to notice?